Okay, question 1. We have a random sample of 20 hobbits from a normal distribution, and Gandalf wants us to find unbiased estimates of the mean weight, the variance and the standard error of the sample mean. So this is quite straightforward. We've just got to calculate a weight. So the sample mean, x bar, is the sum of x over n, which we know is 1347.2 divided by 20. I'll just do that on the calculator. And we get 67.36. I'm just going to put that into a memory because I'm pretty sure I'm going to use that. I'm going to call it m for mean. So whenever I need that, I can just use m. So that's 67.36. And I'm going to call that 67.4, seeing as it's 3 sig figs. Part 2. Unbiased estimate of the variance. Well, we've only got a sample, so we have to do the sample variance, s squared. And again, we just have to remember the formula. It's the sum of the squared distances from the mean divided by, in this case, n minus 1. So that's 748.758 divided by 19. So back to the calculator. And we get 39.408, which is 39.4 to 3 significant figures. Now I'm just going to square root that number because that's that will give us s, sample standard deviation, and I'm going to store that into s. Because again, I'm pretty sure I'm going to need that 6.277. And thirdly, in this question, the standard error of the sample mean. And again, another formula, standard error of the sample mean is s over root n. So in this case, 6.2776 divided by the square root of 20. Back to the calculator, and I've got s stored, so s divided by the square root of 20. And I'm going to store that as well. I'm going to store that as e for error, again just in case I need that, and that's 1.40. Notice I'm giving my answers to 3 significant figures but using exact values. So that's part A. We can move on to part B now, where we're asked to find a 99% confidence interval. Now we've got a normal distribution, a small sample with an unknown standard deviation, and that tells us that we're going to need a t distribution. So it's going to be x bar plus or minus t times s over root n, and s over root n is what we're calling e, the standard error of the mean. So x bar, we're going to need t, so degrees of freedom is n minus 1, which is 19, and it's a 99% confidence interval, so we're going to need the 99.5 value from the table. Now I've just got the formula book up here, and I know that the t distribution is on page 26. So we want 99% in here, so we've got 0.5% here and 0.5% down here, so we've got 99.5% that we're looking at. So I'm looking in this column, the 99.5% column, and I need to go down to row 19, and there we get our value of t is 2.861. So I'm just going to write that down, t equals 2.861. So the confidence interval is going to be 67.4, only I'm going to use my exact value, plus or minus 2.861 times s over root n is 1.40. Again, I'm going to use exact values there, so just get my calculator up. So we've got mean, start with the lower end, so minus t 2.861 multiplied by s over root n is what we're calling e, and that gives us 63.3 for the lower value of the confidence interval, 63.3, and the upper bound is going to be the same calculation, but just change that minus to a plus, and we get 71.4. So those are the upper and lower bounds of the confidence interval. I'm pretty happy with that question. So part C. Work by a previous researcher, Radagast, finds a 99% confidence interval to be 61.59, which is less than that, and 69.83, which is in that interval but less than the upper value, so there's some overlap. And we're asked to find the sample mean for Radagast's sample. Well, it must be halfway between the upper and lower values, seeing as the distribution of this is symmetrical. So we just need to do halfway between 63.3 and, oh, not 63.3, 61.59 and 69.83. Press equals, divide by 2 and we get 65.71. Nice straightforward question for part 1. Part 2, comment on the claim that the hobbits are getting heavier. Well, bearing in mind that this is the older, previous sample mean with a confidence interval, well, the mean has increased. Gandalf's mean is 67.4 and Radagast's is 65.71, but that's just the sample mean. The confidence intervals overlap, so we don't know that they're getting heavier. That's the whole point of a confidence interval. The mean could be anywhere in there, so we're just going to say we can't be sure. Since the two confidence intervals overlap. And that's that. Okay, now part D. Gandalf would like a narrow confidence interval, and he's planning to take another random sample of n hobbits weights in a year's time with another 99% confidence interval, and this time he'd like the width of that to be no wider than 5 kilos, and we're asked to find the least value of n, the number of hobbits he needs to sample. Assuming Gandalf performs a z-test with the value of the variance to be the one we obtained in part A. Now I can see why he's going to have to make that assumption, because he doesn't, in order to work out n, he needs to know the variance, so he'll have to assume it's that, since that's the only value we've got. And I guess if he takes a big sample, which I suppose it will be, then it'll be big enough that he can assume that the sample variance is the population variance. So we need to know what n needs to be. Well, we can work out what the z value is going to be, so I'm just going to go back to the tables, and I'm on page 26. If I just flick back one page to page 25 where the z values are, we can look up the 99.5 value. It's down here, 99.5, and it 2.5758. So z equals 2.5758. We know the value of sigma squared, that's 39.4, we're going to call S squared to get the exact value. Now the width of the confidence interval is the upper value minus the lower value. So the width of the confidence interval is the upper value, which is x bar plus z times sigma over root n, minus the lower value, which is x bar minus z times sigma over root n. And we want that to be no bigger than 5. Well, this is an inequality that we can solve. If we simplify the left hand side, the sample means cancel, and the minus z sigma over root n gives us 2 z sigma over root n, and that's got to be less than or equal to 5. Now we know z, we know sigma. I'm going to leave them as letters for now because I think it's going to be easier, but we can rearrange this equation to find n. We can see that if we multiply both sides by root n and then divide by 5, we end up with the inequality that root n has got to be greater than 2/5 of z sigma, which we can square to give us that n has got to be at least 4 over 25 times z squared. Now I'm going to put the values in because I know them. 2.5758 times 39.4, where 39.4 is s squared, the exact value, and that equals, calculator time, 4 divided by 25 multiplied by 2.5758 squared. Actually, I need a squared on here, don't I? Multiplied by s squared, and that gives us a value of 41.83. 41.8. So we get the n, the least n, is 42. And I'm just running out of room. Hopefully you've got a bit more room than me, but that's the answer. Great. Now that's the end of that question. I'm just going to show you where the marks are here. We get a mark for this, and 1 mark for this, and a mark for this, and part B is actually 4 marks in total. There's a mark for the right t value, a mark for substituting the numbers in, a mark for this 1.4, and 1 mark for the values of the confidence interval. Part C, we get 1 mark for the sample mean and 2 marks for this part, 1 for the can't be sure and 1 for the reason. And then this last bit, although it's quite tricky, there are actually only 3 marks available for this. We're getting 1 mark for setting up this equation here, 1 mark for simplifying it to this calculation, and then 1 mark for stating the answer that the least value is 42. So that's question 1 done, and we're ready for question 2 now.